Hi, everyone. Welcome back to our third office hours, our second with Eric. This week, we're going to be going over a couple topics that Eric and I discussed after our last meeting. Specifically, Eric will be going over ADT and layers and possibly doing a long form demo. So I just want to reiterate that every Tuesday and Wednesday, we're going to have office hours. On Tuesday, it'll be 15 UTC. On Wednesday, it'll be 1 UTC. And tomorrow, we'll have the second meeting with Rusty. Next week, we'll have new subject matter experts, so new topics and new talking points. If you do have any questions, make sure to join us on Discord, reach out to us in the general discussion of Silvermint. Just post any questions you might have and we can go over them. So without further ado, I'm going to pass it over to Eric so that way he can get started on his demo.
Great. Thanks, Nikki. So I'll share some slides first just to kind of refresh a little bit on what we covered, some of the stuff we covered last week. And let's see, that'll be some groundwork for the demo. Okay, so hopefully everybody can see this.
Yep, we can.
So the idea, we left off last week an overview of what Symmetry does and why, and the journey that we've had so far. Today, I thought we could talk a little bit about how you actually use it, and in particular, how you might apply it to legacy code, because this is probably a very typical scenario where somebody already has a large body of code, and it's typical code, and you want to impose some order on that and add some safety to it and use some of the Symmetry features to do that. So that's what we're going to show today. So a little bit of refresh about what Symmetry is and what we've done with it. So there are really kind of boils down to three different types of language extensions that we've added to Go. So we took plain vanilla Go, and then we add some language extensions and features to it to allow more safety and verification. So the three ways we do that, we add these things called asserts, which uses a Z3 solver. We add these things called layers, which allow us to reason about portions of code and give them some attributes that we can reason about. And then we have these things called algebraic data types, which are really just nice ways of grouping types and structs and creating a little bit of privacy around them. So we'll see that in a second. So Z3, if you don't know, is an open source SMT solver from Microsoft. It's one of the better ones and pretty robust and bulletproof. What it really allows us to do is to make some assertions about our code. So we want to say some things that we believe are true about our code, and then we send it off to Z3, and Z3 crunches on our statements and the assertions and determines whether or not what we said is true. So very helpful for making some statements about your code and making sure that it's provably correct. And a lot of people ask, okay, well, how's this different from testing? But testing is fine, and we should still do testing, of course, but testing is kind of a scattershot approach. It's very difficult, at least, to say for certain that your code is bug-free. You can say that I haven't found any bugs, or you can say that I have found bugs, but you can very rarely say that I guarantee there are no bugs. The prover actually uses math and assertions and a lot of crunching on the computer to look at the things that you're saying, your statements that you're making, and the assertions that you make about those statements to actually verify that what you're saying is true. So it is more correct than testing. Layers are a way that we decorate the language. We add these, we call them layer marks, and they say certain things about the language. And then we go through the actual syntax of the language and the code. Again, we're analyzing the code, and we determine whether or not those marks are holding for the code that we mark. In particular, we have three right now that we use. Core, which is the most restrictive. And a way to think about core is that there's no mutation and no randomness. So nothing's allowed to change. You can't change state, and you can have nothing that's adding any randomness or non-determinism into your function. Stateful is a little less restrictive. It's kind of like core, but also adds a few more things. It does allow mutation, but there's still no randomness. Full is the most expressive, more like pure Go. And the way to think about full for our purposes is it's full Go. once it gets to the blockchain, we might need to clamp it down a little bit more to get rid of deterministic threading and things like that. But for now, just consider it to be full Go. An ADT is really, it's just a tagged composite type. So we're going to have all these type structs, and we kind of lump them together, and then we're going to bind them together with a private interface. And the reason why we do that is to the private interface assures us that we can't accidentally add more or intentionally add more types to that structure because they don't know about that private interface. So it gives us another way to assure ourselves that our code was correct. And once again, on our approach and how we do all this stuff, we take the standard Go and we fork it. And then, so we have this thing that we call Symmetry Go. And then we extend that Symmetry Go, we actually extend the language, most notably the abstract syntax tree, AST, and also some of the tools and tokens and parsing and everything that goes along with that to accept our new language extensions. And then we can use that extended Go, our Symmetry Go, to create the Symmetry transpiler, because now we can say, okay, this thing knows about our new extension called SymSum or our new extension called layers. So now the user doesn't actually need our Symmetry Go. All they need is the Symmetry transpiler that we end up with. And so you can see on the right there how Symmetry is used is that you create a .sim file, which is really just a Go file that has the ability to contain our extensions. You run that through our Symmetry transpiler. It does the analysis and then spits out normal Go. And then your normal Go can run through a standard Go compiler and create an executable or run directly or whatever. And we've tried to kind of make it look a lot like Go. So, Go has, for instance, lots of little commands, subcommands that you can use, like Go run or Go build. And we've carried those along in Symmetry as well. So you could do for instance, Symmetry run, and that will actually do the compile behind, or the transpile behind the scenes, create the Go code, and then run it through the Go compiler for you. So it all looks fairly seamless. So that's what we're going to show today. So now I'm going to stop this share and switch over to a different window. Okay, can everybody see that? And can you read it?
Yeah, I can read it pretty well.
Perfect. Okay. So what I've got here is a little project that I wrote a few months ago called Ledger. And the whole idea behind Ledger was that I can create accounts, and these accounts can hold some value in a state. And the reason I'm pushing the state separately or holding it separately is because I want to be able to pop that state onto a stack and then pop it back off again, so I can kind of manipulate the state directly. And let's see, what else? Oh, I'm using a message structure, so nothing happens directly. It all goes through messages. So a message is created, and then it's put into, there's a separate Go routine that handles the message pump. And then let's see if I can find that. That's not important, but here are some of the messages. So in particular, I have a message null, which just prints something. There's a fun message, which only the administrator can use. There is some stuff to handle checkpoints, which is the popping off and pushing on to the stack of the state. And then print, and then there's transfer. And transfer is how you transfer value between two people. So there's message type. Here are the different message types. And anyway, I don't want to get too far into how this works, because the whole idea of this is, again, it's legacy code. It's something that I wrote a few months ago. I maybe not quite as familiar with it as I was back then, but now I want to start to impose some order on this project and do some verification and validation on it. So here down at the main, you can see here's testing the whole system. So you see I create the message queue. Here's the Go routine when it starts the message pump. I create a new system level identity here. And then I start creating messages and testing stuff. So here the system created itself and then creates funds for itself. It creates 1,000 units of value for itself with this fund message. And then down here, the system creates 2 new accounts called Bob and Alice. So here's Bob and Alice. And then it prints the value of their accounts. And then stuff starts happening. So here you see Bob and Alice start funding each other. So here you've got, oh, sorry, here's the system setting up funds for Bob and Alice. So for here, the system transfers 50 units to Bob and 100 units to Alice. So that starts them off with their accounts. So that's the equivalent of them making a deposit and the banker saying, okay, I put that money into your bank. So here's where the fun starts happening. So here, Alice transfers Bob through the messaging structure, 13 units. And here we do a rollback checkpoint. So we're just setting a checkpoint that we can roll back to if we want to. And then here we have Bob, let's see, transferring 7 units to Alice right here. And then we restore a checkpoint. So here we're actually doing a rollback. And then here we're, since we've reset that again, we're now resending, Bob is resending that $7 to Alice. And then here we're just saying, okay, let it go through, remove that checkpoint. So basically just kind of going through and checking everything in our legacy code. So let's give it a quick run here. And we're going to be over in the terminal on the right-hand side here. We're just going to use a typical Go command, go run main.go. So there we go. We're going to run it. And let's go back to the very beginning here, and we can track all of those things. So here we are with our go run. And you can see a whole bunch of messages are sent because they get sent immediately, and then they start getting processed as they work their way through the queue. So the first one, you see system created. Here's just a little comment, systems created, it funds itself. So in here, you're seeing that funding of $1,000 to, or 1,000 units to the system. And then you see the system making the Bob and Alice accounts here. And they initially start out with 0 value. You can see that here. And then the system is funding both Bob and Alice. So this is, again, the equivalent of them making a deposit into their account. So here you've got $50 system giving to Bob and $100 system giving to Alice. And then we look at their accounts, and sure enough, they have 50 and 100. And then here we go. The first interesting thing that happens here, Alice transfers some dollars to Bob. So here you can see she's transferring 13 to Bob. And then you look at Bob's account. Bob now has 63, 50 plus 13. Alice, we've decremented her from 100 down to 87. So everything looks good. The message pump is now full. So now everything that's backed up, or it's, sorry, empty. So now everything that's backed up starts sending again. So more messages start pumping through, and then you see more stuff happening. So basically you could, track along this whole thing and go through the main and look at all the things that are happening in this ledger system. And again, this is, my little demo ledger system to test a bunch of things that were happening. But, it's like 600 lines of code or so. So if you look at it here, let's see, what are we at? Yeah, 602. So exactly 600 lines of code. And there's a lot of stuff. There's Go routines happening here, lots of different types, messages happening, methods here, all kinds of stuff. So it's, I think, charitably, you could say it's kind of messy. And so we want to start imposing some order on this thing. We want to start using symmetry to tame this beast. So now I've got a little sim file. So what I would normally do here is I would take my main.go and I would rename it to main.sim, and then I would start working on my main.sim and using that as my main file. So I've done the equivalent of that here. I've created a main.sim. So here we go. Pretend like I just took main.go and copied it over. In reality, I added a few things because I didn't want you to watch me type all this in. So what I've done here is, one thing you might want to do with a ledger account of this kind is you might want to have a very basic thing that says, I want to know when the amount of value in the total system is changing, and I want to track that. So whenever there's any kind of transaction happening, I want to make sure that that balance remains the same. So if the system starts out with 1,000 units and then all these transactions are happening, I want to make sure that those 1,000 units haven't inflated or deflated. That remains constant. So money can move around, but I don't want it to change. And if it does change, I want to know about it. So that's the order that I want to start imposing in my little demo here. And I want to use Symmetry to help me with that. So the first thing I'm going to do is I'm going to add this little watcher. And so I'm creating a SimSum, which is again this ADT. And I'm going to create a struct inside of that guy, which has total value. So this is the total value in the system. And then I'm going to hang a bunch of methods off there, which I want these things to be very safe and protected, to keep track of that total value. So here, for instance, we've got a get, which just returns the total value. You can see that here. I've got a set, which sets that total value. I've got an add, which adds some new amount to that total value. And I've got a check. And the check says, look at the total value and compare it to this thing I'm passing in and send me back a true false, whether or not those things are equal. And then I've got one more little function I'm adding here. And this, you'll see how this is useful later. But what this guy is doing is he's saying, I want to sum up the value of all the accounts in the system and return that total. And obviously you'll see that. So then I set up a W here, which is the watcher. I initiated here. Okay, so that's that guy. And I'll show you in a minute how this breaks apart into the ADT in real Go. Okay, so now I've got, so I've got this thing set up, which is my watcher. And now I want to actually use my watcher. So I'm going to create a new message. So I've got my message pump and my message types here. So I'm going to create a new message, which is a check message. And the whole idea behind the check message is that he can now use this watcher that I've created to run a check on my ledger. Okay, so let's look at the fun. The fun message is the existing message that's already there. And this is the guy that says, I'm adding new money to the system. So that's the first thing we want to graft into, is we want to make sure that we have an add here. We're using our watcher add to add the value that's being added through this fund message. So again, we're just integrating into the message that's already there that keeps track of all the funding. And again, add up here is right here. And he says, okay, if any value is being added to the system, then add it to my watcher total value. Okay, so then now we're setting up the actual check message. So here we have the check message. All it is pretty much a null message with a body, and then it satisfies all the interfaces required of the message. You'll notice that there's a few things I've done here. Now I've begun to use Symmetry to mark these methods that I'm creating, these new methods. So I'm making sure that all the new code I write is safer than the legacy code that we're working from. So you can see here in my watch, I'm using SymSum. In my get, I'm saying that that's core, which means that it does not mutate. I'm saying that my add is stateful. Why is it stateful? Well, because it's changing value. This plus equal is an assignment, and that's the mutation. So we've got a value change there. And in fact, if I didn't do that, I'll actually show you that. It'll flag it as an error. Again, here's another core. So this guy is just doing a bool and returning the value of the bool. So he's not changing anything. So he can be core. And this one is full. And I'll show you in a minute why that is full. But basically, he's calling something outside. Okay, so let's go down to our new message here. Likewise, I'm marking the functions here to assert some statement about that function. So here again, I'm saying that this type is, if you look at it, it's just returning the type of the message. So I'm saying he's core. He's not changing anything. And the message body here is returning just the message body. It's not actually changing anything, just returning some value. So he is also core. The mark is doing an assignment. You can see it's actually changing something here. And so he's actually stateful. And then the copy message likewise is doing an assignment. So it's stateful. The check message, which is the message type, is stateful because also it's doing an assignment. And then this guy is full. And the reason he's full is that he is going print, and print FMT printf is not layer marked. And so something that has layers cannot call something that doesn't have layers, excuse me, unless it's full. And that's just a safety mechanism that says you're calling something and we don't know what that thing is. And that thing could be changing state. So we want to let you know about it. Okay, and then down here at the bottom, then we're just beginning to use that check message. So here we create a new message of that check type, and then we just use it. So here we're actually sending that to the message queue, which is going to instantiate that message. Okay, so that's kind of basic high level of how we've taken our legacy code, our ledger system, and we've put a watcher on top of it, and we inserted one new message to use that watcher to check the value. So now let's give it a go. So we looked at the first one here with main.go. When we ran that, we said run main, run go run main.go. So now we're going to do the same thing, but we're going to use Symmetry. And now we've got our sim file. So our sim file is here. Let's go use that. So let's go Symmetry run main.sim. So same basic command structure. We're just using Symmetry in place of where we would use go. So we'll go ahead and run that. And it's going to crunch away, do the analysis, and a few things. Well, let's look at this first. So where did we start? Here's where we started. So again, here's our message queue. It's it's receiving a bunch of messages, and then it begins to process those messages. So here's the first one where the system funds itself. And if you look down at the very bottom here, or I begin to do that. So here we are, here's the check. And then right after it funds itself, I think I look at that. So here's the initial, yeah. Yes, so here we go. So here I fund it, and then I look at the value, and so it should tell me that there's a 1,000 in there. So here we do look for our check. Yeah, and here it is right here. So here, this says that I expect there to be 1,000 in there, and there's 1,000 there. And that's because I've funded it right here. And then I've sprinkled some more checks throughout this code. You can see here's one here, here's one here, here's one here. So I'm just using my check message throughout my test. And now we can go through and we can see what's happening here. So here's a check. Here's a check. So yeah, it says 1,000. So the system hasn't changed. And I go through more. Here's a check. Yep, still 1,000. It's all the same. And go through here, still 1,000. And I think that might be the end of them. Oh, no, there's one more. So here's another one. So check, check, check. So all the checks are panning out, which means that my little watcher is working. He says, I believe that there is 1,000 units in the system. And even after one of these transactions is happening, and I really don't know what's happening with them, but I've protected them with my watcher, and now I can see that those are holding true. Okay, so now let's look at what's actually happening behind the scenes here. So if we come back, so remember we said this is a transpiler. So the transpiler is taking a source language of Symmetry and creating a new source language of Go. And so we would expect to see some new stuff in our main.go, which is true, because what it's really doing is taking the Symmetry as now the ultimate source of truth, transpiling that, creating that Go behind the scenes, and then running it. So that's all the stuff you saw happen over here. And here is the actual Go. So if we look at it, that SimSum that we have here at the very, very top, right here, this guy, he transpiles into this. So there's a watch interface, which has this private interface, and that's the thing that keeps it safe. It's basically a big number, token if you want. And then here's the watcher struct, which has the total value. And now I've got all these methods, which are part of that type system. So now I've got a watcher method called get, called set, called add, called check. So these are just some new methods that I hung off of that watcher struct. So all those things are still there, and all the code that I put in there is still there. So it's basically taking all the code that I created here, turning it into the abstract syntax tree, the AST, transpiling, rewriting that AST, and then regenerating the code back into Go, and then running that code. So that's what's happening.
Way cool. Eric, do you want to open it up for questions now?
Sure. Yeah.
Okay.
Yeah, we can do that.
Yeah. So same thing as last week. If you guys have any questions, we'll leave it up to you. So that way you can ask Eric. He can answer different levels of questions at different styles. So if you have anything, I'll open it up for like an open forum for the next few minutes.
Yeah, so what I wanted to do here was just kind of show how you might really use Symmetry. And again, a lot of people have legacy code, something that might be not as pretty as they would like, bigger, less organized. And over time, we want to start taming that code and making it more secure. Oh, I wanted to show a few errors as well. So let's go ahead and look at some of that. So if I come back here to the symmetry file, and let's say that I believe this to be not full, but I believe it to be stateful. So now if I run symmetry, it's saying range over map in stateful. Okay, so well, why can't I range over a map in stateful? Well, okay, I declared this as stateful, but remember that we said stateful does allow state change. It allows mutation, but it doesn't allow randomness. Okay, so what's random? Well, it turns out that maps are ranging over maps is random. And if you don't believe me, you can go out to the Go programming language spec. And if you look under ranges and you look at point number 3, iteration over maps is not specified and is not guaranteed to be the same from one iteration to the next. So of course, what that means here is that as I range over this directory, which is a map, it's not guaranteed to be in the same order. Now, that doesn't impact me now because I'm just running up the total. But if I relied on the order of that, that would impact me. So this little error is telling me, okay, you thought you didn't have randomness in your function, but you actually do. So, so that's actually full. Okay, and let's look at another one. So let's come down here and say, why is this check function full? Let's make that, well, first let's make it core. Say, I think it's core. Well, actually it's not. Okay, so what's going on here? So there's a few things happening here. One is I've actually got no assignment errors because these are new values. So because they're new values, this is a short var decal. It's not an actual assignment. So those are okay. But what I do have is I think that I'm saying this thing is core, but it's calling this function called w.sum. And w.sum is a higher level function. You recall that we made that guy up here. Where is he? Here. We declared him to be full. And so I can't say that this thing is core if it's calling a function that has a higher level, because then I can't guarantee that that thing I'm calling is not mutating. Let's see, I've got another problem here too, which is this thing called FNT printf, which is a standard built-in for printing. But since I've not marked that function, it's a system level function, I can't guarantee that it's not changing things. So again, I've got these two errors that are happening. So that's why this guy, well, actually, let's change it to stateful and see what happens just for fun. Yep, same stuff, because they are indeed the same error. So let's make that full. And now everything should work. There we go. Nice. So you can see how we can assert these things about our code, and then Symmetry can verify it for us. So even though we are human, we make mistakes, the almighty computer supposedly doesn't.
Eric, Paul has a question actually.
Mm-hmm.
I don't know if Paul wants to ask it, but he actually wrote, he's curious how an error could be introduced. Example would be like if the total value becomes 1001 instead of 1000, is there a fix to approach that? Or do these assertions quite literally prevent this from happening?
Well, in my code, they do, but it's not as nice as I would like. And so I'll show you why. So let's go through here, and we're saying that we've protected these functions, these watcher functions. We've protected them all. We're looking at them. We've said things about them that we believe is true. We have one place where we set the value. We have one place where we add the value. We have one place where we check the value. Very simple functions. We've marked them with our layer values. So we're adding another layer of protection on top of that. We've created them as ADTs. So we know that they have these private interfaces. So nobody else is going to be using that, adding to that typeset. So, so that's good so far. Now, where the one area where you might say it's a little iffy is right here, because what I'm saying here is that my fund message right here is the only place where I add value to the system. Well, that may or may not be true. So there might be somewhere in this code another area where I increase the value, the total value of the system, and I don't know about it. I've kind of scoured the code and I've done a look through, and I'm reasonably certain that this is the only place, but I could be wrong. So yes, I'm reasonably certain that this is correct. But if we go back to all three things that we're adding to Symmetry, the one that I'm not showing today is Z3, and Z3 would allow me to say even stronger things about my code. In that case, I would be able to make some assertions that would do the actual analysis of all the code, and I would be able to assert, for instance, that the total is equal to my total that I'm keeping. So that would, once we have the Z3 stuff up and running, we'll be able to make even stronger assertions.
Thank you. Yeah, well, as it got more and more complex, I was wondering if there were some, because I did notice that it looked like it was when you did the actual value set. It looked like it was stateful, which I suppose would that enable?
Yeah, the value set is stateful.
Yeah, would that enable it to be updated? Because I noticed it does allow for mutations or changes inherently.
Yeah, again, the layers give us a way of marking our code and thinking about our code. So for those functions that do mutate, I have marked them as stateful or full, and that tells me at a glance, okay, this thing is changing state. So it lets me know exactly where I change state, exactly where I don't, exactly where I could have randomness, and exactly where I can't. So I mean, that's the value of these layer marks.
Gotcha. Thank you.
Eric, I have a question, actually.
Yep.
So as we're talking about these different layers, do you imagine then someone who's making like a smart contract to, fully utilize full and then start pulling back to stateful and then core, or how do you actually imagine that in the team using it?
Yeah, I mean, that's exactly how, I mean, if I was to do this, so the first level of how I attacked this problem was to just, okay, at a top level, I want to make sure that the total value of the system isn't changing to the best of my knowledge. And then I want to, and then I'm going to use, after that, I'm going to use Z3 to also, crank that down a little further. And then I'm going to start going through and I'm going to start changing the code to be generally more safe and more secure. And the way I will do that is I'll start taking some of these types and I'll turn, some of these into ADTs, and I'll start marking them with different layer marks and making assertions about them. I'm going to have to rewrite some of it. I'm going to have to refactor some of it because otherwise it's all going to be full. So I am going to have to, rewrite some of it and refactor some of it and pull some functions out. But this gives me a template and a way to do that I can begin to change my code. And I'm going to do it iteratively, just like I did here. I didn't try to change everything all at once and try to make it all, pristine and secure, because that would fail. So I'm going to take a little bite at a time. I'm going to add stuff, little changes at a time. So now, I'll check this in now, and this will be my new base to start from that works. And then I'll maybe take the account structure and I'll try to add some layer marks to this, and I'll add grab some other functions down here, and I'll start adding layer marks to these. And I might have to refactor some of them, but I'm going to just chip it away at it and make it safer and safer and better over time.
Cool. Thank you for that. Again, open forum. You guys can shoot out questions fast as rapid as you guys want. So Eric is here to answer all of them.
Yeah, I had a question about how once the Z3 portion is implemented into this, like what will that add in terms of these other layers like stateful and full? What does Z3 bring to the table?
Sure. Yeah. So let me actually stop sharing this and go back to a slide, because it'll be an easier way to show that. Okay. So again, Z3 is an SMT solver, so it allows us to send over some statements and then some assertions about those statements, and it will verify whether or not they're true. So a little example of that is right here. Yeah, that's visible. So here you can see I've got this function called add1, and he takes 2 arguments, an a and a b, which are int 16, and returns 2 returns here, and both of them int 16s. So basically what it's doing is it's saying that I've got this a and b coming in, and I'm going to create this c and d, which are that thing plus 1, and then I'm going to return that c and d. So you can, that's why it's called add1. So it takes these 2 things and adds 1 to each of them and returns the result. So what I'm going to assert about that is that C is always going to be greater than A, and D is always going to be greater than B, which, you know, on the face of it, you can say, well, that makes sense, right? Because C is equal to A plus 1. So naturally, C is going to be bigger than A, and D is equal to B plus 1. So naturally, D is going to be bigger than B. So I think that assertion is valid. So now what we're going to do to check that is we're going to use our Z3 assertion inside of Symmetry called symassert. And symassert says that wherever I see a symassert, I'm going to look at the things leading up to that symassert, and then I'm going to use those to validate that that symassert is true. So when I run this, it's going to say, it's going to take this function, it's going to look at that function, analyze the function, grab these 2 things here in the data types, send them over to Z3, grab this stuff in here, create those as assertions, run those over to Z3, and then it's going to try to find a failure case for which that's not true. So you can see over here, we send over, this is all the stuff that we send over to Z3, and this is called smtlib. So it's just a syntax for dealing with Z3. So here we're declaring a constant A to be a bit vector of 16, which means it's just a 16-bit integer, and B likewise, and C and D, and this thing called X, which is just our plus 1 over here. So it asserts that X is equal to 1. It asserts that C is equal to an add of A plus 1, and D is equal to an add of B plus 1. And then it asserts that there is no case for which C is not greater than A and D is not greater than B. I think I said that right, but there's a lot of negatives in there. So, and then it checks that, checks to see if that assertion is satisfiable, and then if it's not, it gets a model. So what ends up happening then is it says, okay, I looked at that stuff, I checked, you know, these constants that you sent, or these types that you sent, I checked these statements that you sent, and I checked these assertions you made, and I actually found something that's not true. And the thing it found, you can see down here in its return language here, is that there's this value for B, which is 7FFFF, which is hex. So it's, I think, 32767, I believe. And then there's this other value for A, which is 32767. And there's this value of C and D, which are 8000 hex. And when those things happen, then your assertion failed. And we're scratching our heads wondering, why did that happen? Well, the reason it happened is because these ints are actually signed values. So once, you know, half of it is negative, half of it's positive. So when I hit the halfway mark at exactly that point where either A or B is 32767, then it's flipped over, and C and D are now 8000, which is negative. So it said, okay, I looked at that stuff and I figured out a case for which it's not true. So that's, you know, the value that Z3 will bring to the table is analyzing our code, and now not you know, monkeys on keyboards making tests for it. It's actually looking at the mathematical validity of the statements we make.
Okay, and I had another question that brought up. So is this checking these assertions after this block of code is ran, or like, let's say before you assign C to be A plus 1, you had A equals C plus 1.
Yeah. So what's happening here is these are all compile time. So it's actually doing all this stuff when you run the Symmetry analyzer. So it's happening before you are even done compiling the code, before it even gets to go. And so The reason we have to do this is that the stakes are high for blockchain, because once you create, for instance, a smart contract and you put it in the blockchain, it's baked, it's done. So we want to catch all these errors before they get in there. We don't want to test them after the fact. I mean, we still will do obviously some standard legacy style testing, but we also want to be able to reason about our code before it even creates the executable. So that's what we're doing here. So what's happening is it's actually decomposing this source code into this SMT-lib language that it sends over to Z3. And then that Z3 analyzes that actual code language, the statements of the code language and the assertion, and then spits back an answer. So there's no actual Go code running here. It's all running over in Z3. Does that make sense?
Yeah, definitely.
Eric, as I look more into like SMT solvers, like there's clearly kind of like a range, and I've heard on like different forums that there's some that are like more secure or like more, they're better, I guess. What does that mean? Like I'm kind of confused with like the different SMT solvers and like why and I kind of asked this last week too, like why we chose Z3, but I'm still trying to wrap my head around like how what decisions were made before we decided on it. Like I'm still trying to understand it. Sorry.
Yeah, so I won't say we did an exhaustive search, but we looked at the SMT packages out there, and there were several things we liked about Z3. It's open source. It's been around a while. It's trusted, which is not to say that there aren't others out there that will also satisfy those attributes. But this is the one we went with. It's the one we're comfortable with. I think you can plug in others as well. So it's once you have the ability to decompose your language like this and ship things off to a solver, you can plug in anyone that has the same syntax.
Okay.
But it's a good place to start. I mean, obviously we're new. We're in the very first stages of getting the Z3 stuff and all this stuff running, and so we're going to learn more about it as we go. Which is not to say we might change things up and use a different solver later on.
Yeah.
For right now, it's fine. One of the things we've heard about Z3 is that it could have some scaling issues. So if you start throwing a large code base at it and you're sending all the statements and all the assertions at it, it might bog down, because again, it has to crunch through all this stuff. So so we might have to be a little mindful about the things we actually send. Maybe it's just function level assertions that we support, or maybe we have to do some way to pre-test or pre-assert things, and then once we've done them, we don't ship the whole file off, things like that.
Okay. Any other questions? No. I'm trying to think of a few different things, just because I'm trying to wrap my head around how developers are actually going to use this within smart contracts. It's just interesting, just because nothing like this has really been done, and as far as I've known, in terms of like blockchain or even like normal development. Like you've mentioned before that Daphne is kind of utilized this a little bit. Can you, I mean, we're not necessarily speaking about Daphne right now, but what's its use cases in comparison to like something like this?
Yeah, I think the point of Daphne was to integrate very tightly with Z3 and theorem improvers. And I don't know of people outside of academia using Daphne. I mean, there probably are, but I just don't know. So I can't say exactly who's using Daphne and why. I only know that researchers and academics are using it.
Yeah. Cool.
I mean, the whole idea behind Go was, we know it's a really good language. It's a strong language. It's a mature language. It's been around a while. People like it. It's a systems level language. It's general purpose. The compiler is very fast. The executable is very fast. It's got a pretty easy learning ramp to it. So for our purposes, it seemed like a great language to build off of and to extend. And that's proven true. I mean, we use Go in the network. We use Go in the Symmetry Go compiler. We're extending Go. Go itself is nicely written, so it's more easily extendable. So it's got a lot of nice attributes to it. Z3 is a very nice theorem prover. So we're kind of taking that, peanut butter and jelly and pulling them together and strengthening our symmetry compiler, the transpiler.
Cool.
Now, I had another question. In terms of what the developers who will be using Symmetry will be expected of in terms of Z3, is this something that is done in the background? Like, are these assertions created by Symmetry, or is this something that the developers will be expected to implement into their code?
The latter. So if you look at this example here, my normal Go code looks like everything without this. Oops, everything without this. So normal Go code would say, okay, I've got this function called add one, and it's got these two parameters and it returns two values. And here are those two values it returns. So that's what your normal code would look like. And then as a developer, you would add all this highlighted stuff. So you would add this symassert, which is a keyword. That's our language extension. So we added a new keyword to Go, which is symassert, and it's a block. So it has this open block and closed block. And then there's a bunch of statements inside of this, which are the assertions. So once the symmetry analyzer sees this symassert keyword, it looks at the statements leading up to that. In particular, inside of this function, it's going to look at this statement and this statement and the types that they reference, the C, the D, the A, and the B. And it's going to take these assertion statements inside of the symassert, and that's the stuff that it's going to package up and send off to Z3. So it's kind of automatically all happening when you put this new symassert keyword in your code. And you can you'll be able to make assertions about any of your statements as long as it's a variable that exists, and we can make some mathematical statement about it. That's a valid assertion.
Cool. I'll leave it open for one more minute, and then we can, if there's no more questions, we can end there.
I guess I'm a little bit curious about how much more resource intensive running something like Z3 in that case, where you're doing something similar to just doing an assert statement and something like JavaScript. How much more resource intensive are all the tests that Z3 is running to really prove that assertion versus something just like running a few test cases where you might miss that that one case that isn't obvious, where it contradicts the assertion.
Yeah, for something this simple, it's pretty quick. So it's got a couple of statements, a couple of types, and a couple of assertions. So in this particular case, it's pretty quick. But that is one of the things that the Z3 researchers told us that we probably will run into as we have larger and more complex bodies of code, is that we're going to have to be more mindful about how much overhead we're pushing off to Z3, because it does have to analyze that and crunch through it and mathematically prove the statements that we're making and find failure cases as well. So the model is also returned. So yes, I mean, I think it's a valid concern that is something we're going to have to be mindful of. But I think in the simple case, at this point in some of our testing, we believe that probably if we restrict it to the function level at a minimum, then it should work fine. I think we can't prove that yet, but we kind of think, based on what we see right now, that at least proving statements within functions should be doable. Proving the validity of something that depends on the whole body of source code, yeah, that's probably not doable on day one.
Sure. I guess I'm also just a little curious, like how many different values, if that's even the way that it approaches trying to make that assertion, how many different values is it checking, and does that determine by the function itself and just how many possible inputs it can take, or does it have some sort of optimized way of determining the validity of the assertion?
Yeah, I mean, it will take all the values that you give it and try to prove or disprove your assertions. So basically, you have to give it enough information to reason about what your assertions are. And if you haven't done that, it's actually not you that hasn't done it. It's us that hasn't done it. It's because we screwed up and somehow putting their SymAssert keyword in there that didn't find the right statements or something. Or it could be a bug in the code as well. But let's say in this particular function, it has all the information it needs to make to prove or disprove the assertions. So here you go. It's got the types of the A and B. It's got the types of return values. It's got the mathematical statements which lead up to that, which are C equals A plus 1, D equals B plus 1, and then the assertions that C is greater than A and D is greater than B. So it has all the information it needs to disprove that. And there could be a case where you make some assertion in here, and maybe I said instead of this, I said E is greater than A. Well, obviously that's going to break, right? Because there's no E here. And if I'm expecting it to go back outside of the function and get some E value that's a global, it's probably going to say I don't have that value.
Gotcha. Thank you.
Cool. All right. Well, thank you, Eric, for being our subject matter expert for these first two meetups. For everyone watching on YouTube, there is a first video with Eric explaining the overview of symmetry and layering. So make sure to check that out. And for anyone interested in like our validator talks with Rusty, who's actually in this call, he just poked his head in. That will be tomorrow at 1 UTC. And for all those local to Utah, that's Mountain Standard Time, 7 p.m. So come with your questions or ask them before we get in there, just so that way we can have some stuff prepared for you. Thank you guys for joining. But that's where we'll end it today. Thanks, Eric.
Thank you.
Thank you.